Okay. The homework on first homework of chapter 15, line integrals, will actually be due on Wednesday. In case you haven't seen it, I pushed it back from today. And then the next assignment, 15.3, that'll be due the Monday before Thanksgiving. So for both of those days, so this coming Wednesday and next Monday would be a great time to bring questions on those homeworks. Okay. Now, we'll wrap up with one last thing with fundamental theorem of line integrals and conservative vector fields that I didn't get to on Friday. Let's suppose that F, vector field F, is a force field. So in other words, at any particular point, x, y, z, big F of x, y, z is a force that's being applied to an object at this particular point. And force is a vector, so it has magnitude and direction. Okay. All right. Now, so recall that the work done by this force field F to move an object along a curve C that has parametric equations R of t is your usual x of t, y of t, z of t, and t goes from A to B. So this is a generalization of the usual formula for work. Work equals force times distance. It's just the line integral of a vector field F over the curve C. And once we fill in the parametric equations, that is the integral from A to B of your vector field F with the parametric equations plugged in, dot product with R prime of t, which is your tangent vector of your curve C. Then you work out the dot product and so on. So I'm going to focus on an interesting example of this from Newton's second law. What is Newton's second law? Those of you who remember any physics. Really?
I'm trying.
Okay.
For constant forces, force equals mass times acceleration.
Yes. Force is equal to mass, m, times acceleration. Now, if the parametric equations from a curve are indicated by R of t, so R of t is position. So, in terms of parametric equations, if this is position, what would acceleration be? Second derivative, R double prime of t. So f of t okay. Then you're just taking second derivatives of your components, x of t, y of t, z of t. Okay. And this could be called A of t. So then it relates to the form of a Newton's second law is familiar. F equals ma. And that's true, and the way you would have learned it before, everything is a scalar quantity, but it's true if they're vector quantities also. Okay, so if I refer to this line integral, since it refers to work, I'll just call that big W. Okay, so now let's fill this in for our force. So the work is, so M R double prime of t dot product with R prime of t dt. So we still have a dot from before. Okay. Now, this can be written as a derivative, which would definitely make the integral easier to evaluate. But to see that, first m's a constant. We'll assume that, so I'll just pull it up. Now, r has components x of t, y of t, z of t. So r double prime dot r prime would be x double prime, x prime, plus same things for y and z. Okay. Now, what I can do in each one of these terms is make a substitution, a u substitution, to make the integral possible. So let's just break off one of these terms. First one, x double prime, x prime. So I'm going to let u be equal to x prime. So what's your du? What?
Would it just be x and t?
Nope.
X double prime.
Yeah, go the other way. X double prime dt. Okay. So then what you would get is, so we'd have x double prime dt, that becomes du. So this is just u du, well, with new limits. So if I plug in, so this would actually be x prime of a, x prime of b. So now you can go ahead and integrate that. And then go ahead and plug in the limits. Okay, so you would get 1/2 x prime of b squared minus x prime of a squared. Okay. Any questions about that? Now, we'll do the same thing for y and z. I won't write it out here, there's no need. But if we do this for y and z, and then add everything together, all right, so I'll just make a note of that. So your work is now going to be, there'll still be m. So from the first one, I have 1/2, and I have x prime of b squared. Now I'm going to hold off on writing these. I'll put them in later. I'll just move it down here. Okay. And since we have the same things for y and z, I'll just fill those in here. And they're all multiplied by 1/2. So I have that for B, and then again for A. Okay, so that's my work. But now I'd like to write this in a simpler form, because x, t, y, t, z, t, those are components of your parametric equations. They're components of a vector, r of t. So these are the components of r prime of t. But when I take a vector and I take a sum of squares of the individual components, what does that tell me about a vector? It's a magnitude. And because there's no square root here, it's a magnitude squared. So I can write this as 1/2 m, and this would be the magnitude of r prime of b squared minus 1/2 m r prime of a squared. Okay. Now, if r is position, what's r prime? What is the meaning of it?
Speed or velocity.
It's the velocity. So I can write this as 1/2 m v of b magnitude squared 1/2 m v of a squared. Okay. Now, when you have 1/2 mass times, now what's the magnitude of velocity? What do we call that?
Speed.
It's speed, yeah. So what we have here is a speed squared. If this had been velocity in a straight line, then speed would just be the absolute value of velocity. So this is a generalization. Oops, that should be no prime there. So v is equal to r prime. Just says a is equal, acceleration a is equal to r double prime. Now, formula 1/2 mv squared. Does anyone remember what that refers to?
Kinetic energy.
Kinetic energy. So the way you would have learned it, say in a physics course, 1/2 mv squared when you're talking about like motion along a straight line. But this is how it generalizes to the case where you have to take into account magnitude and direction, where everything's a vector quantity now. Okay, so I can write this, because now here we have velocity, this is kinetic energy. All right, so this is work again. So this is I'll call this K of capital B, kinetic energy at the ending point of a curve. So when t is equal to little b, so capital B is the end point of a curve, minus kinetic energy at point A. So this is the initial point. Okay. So in other words, so what we can say, the conclusion of all this, in words, is that the work is equal to the net change in kinetic energy. Okay, I guess net's a little redundant, but okay. So, kinetic energy from point A to point B as the object is being pushed along the curve. Okay. Whoops. Now, that's one way to look at this. But here's another way to look at the same thing. If F is conservative, then f is a gradient of some function, as we covered last time. So it's equal to the gradient minus the gradient of minus capital P, where P is the potential energy. And this is one reason why, when you say the vector field big F that's conservative is a gradient of a function little f, and little f is referred to as the potential function. So that's where that term comes from. So, because it's conservative, we can evaluate work using a fundamental theorem of line integrals. So we have f r of t dot product r prime of t. But this is minus a gradient of p of r of t. So for any conservative vector field, it's this line integral, we don't even have to do anything. It's just you take your potential function and you plug in the endpoints. So we'd have minus p at the terminal point, the ending point of the curve, minus your potential function evaluated at the initial point. So minus p of b plus p of a. So however the potential energy changes from point A to point B, the work done is the negative of that. So if you look back in your notes at the fundamental theorem of line integrals, where in your notes I have big F is a gradient of little f. So in this case, in this example, little f is equal to minus p. So you can see how fundamental theorem of calculus is applied. Fundamental theorem of line integrals is applied here. Okay. All right. So any questions to this point? Now we have two ways of evaluating work. Change in kinetic energy or minus the change in potential energy. Well, it's the same, work is the same no matter how you evaluate it. So certainly these two expressions must be equal to each other. So if we go ahead and set them equal to each other, so the first one was K of B minus K of A, and that must be equal to minus P of B plus P of A. So we have this equation now. So let's rearrange this. Take everything related to point A, put it on one side, everything related to point B on the other side. So I'm going to move this over and move this over, and you get K of B plus P of B is equal to K of A plus P of A. So the total energy is constant. So the total energy, so kinetic plus potential at point A is unchanged from what you have at point B. So potential and kinetic energy individually will change as the object is moved along the curve by the force field F, but their sum is going to be invariant. So this is the law of conservation of energy. So this only applies if a vector field F that describes the force that's being applied to the object to move it along the curve is a conservative vector field. It actually is a gradient to a potential function. Otherwise, you'd still have this no matter what, but you would not have this. Any questions about this? All right. All right, now I can, well, sample this. Start the next section, which I won't finish today. Okay. So Green's theorem is really the second theorem from this chapter. The first was the fundamental theorem of line integrals, that in some way take a fundamental theorem of calculus and generalize it to more complicated geometries, because now we know how to do certain line integrals along a curve. Green's theorem is about integrals over two-dimensional regions. Okay. Now, suppose you have this situation. You have a curve C given by some parametric equations, and this is in this section we're only dealing with two dimensions. So that's components x of t, y of t. Is a closed curve. So we still have t going from A to B. And by a closed curve, the initial and terminal points of the curve are the same. So you have some curve C, and here it might be, depending on the parametric equations, this is your starting and your ending point. Okay. And because it's a closed curve, we have some region here that's a well-defined interior of the curve. So we're going to call that D. So we have a curve C enclosing some bounded domain D. Now, so to move on from the last section, suppose we have a vector field F. If we know that this vector field is conservative, then we have this situation here, and we want the work done as the force pushes an object along the curve. We know it's going to be 0 for a closed curve, because by fundamental theorem of line integrals, which you can use in this case, you'd have little f of RB minus little f of RA. And RA and RB are the same. Now, this was worked out last time, so that's nothing new. What we want to deal with now is what if it's not conservative? Well, we know how to evaluate this kind of line integral for a general vector field F, but depending on F and depending on the curve, it could be quite difficult. So the idea behind Green's theorem is to try to give an alternative approach to evaluating this same integral. Maybe you can get something that's easier to integrate. won't go through the whole gory derivation of Green's theorem. So for that, we'll devote pages in the notes. But what Green's theorem says is, given the situation of drawing the upper board, and C is, now the term I'll use to describe what kind of curves this is allowed for. Is a piecewise smooth. Now, smooth part means that the tangent has a well-defined tangent vector, so r prime of t exists along the curve. But the piecewise part is you can have corners. So these statements slightly contradict each other. So let's just say this exists almost everywhere. So in other words, a situation like this is allowed, where you have a nice smooth curve, and then there's a kink, at so a corner there. So having kinks like here, 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 that's okay. The theorem will still apply. So that's what I mean by say piecewise smooth. Whereas that generic blob on the upper board, that we can just say smooth because there's no kinks in it. Okay. So if C is piecewise smooth, closed curve with counterclockwise, it's very important, orientation. And so in other words, here's your similar generic situation. Closed curve C, interior D, and from whatever point we start from, we move around the domain D in counterclockwise direction. Now, another way to think about this, and this will be important later when we move to 3D, where there's not necessarily a clear notion of clockwise and counterclockwise. If you have someone walking along the boundary, then if they have a proper orientation, the interior of a region should be on their left. So that's how you know that you have a correct orientation. That just happens to be equivalent to counterclockwise in 2 dimensions. Okay. So if you have that situation, and you have a 2-dimensional vector field F that has components P and Q, so the notation I normally use for 2 dimensions. Then what Green's theorem says is a line integral over this closed curve C of your vector field F, which can also be written as the integral over C of P dx plus Q dy. So in other words, P dx dt plus Q dy dt once you fill in the parametric equations. So this line integral over the curve C is equal to a double integral over the interior of D of partial of Q with respect to X minus partial derivative of P with respect to Y. Okay. So in other words, a line integral over its curve. You can think of a curve as basically a warped one-dimensional entity, because one dimension is a line, can be rewritten as an integral over a two-dimensional entity, where your integrands come from the partial derivatives of the original integrand over here. So there are going to be some problems where the objective is to evaluate this, but maybe this will be easier, or vice versa. So like the homework problems or any problems in the final from this section will be about your task to evaluate one kind of integral, use Green's theorem to write it as the other kind, because you're taking derivatives here, your integrand might end up being very simple. Now, so what I plan to do on Wednesday is do some very specific Green's theorem examples, like the kind of problems that you see in homework. But during the rest of the time today, I'm going to show you some interesting situations where Green's theorem can help make a problem a whole lot easier than it would be in any other way. And in both these examples, you'll see why the counterclockwise orientation is a very important assumption. Now, what would happen is, if you got the orientation wrong, it means your integral would have the wrong sign. Because you change the orientation of a line integral, that negates the integral. Okay. I need to mention one other assumption that's required. It's one of those things that kind of goes without saying, but it's going to play a role in this example. P and Q must have continuous first partial derivatives. In the interior. So, because it makes sense because you have an expression dq dx minus dp dy, evaluate all over d. Now, P and Q may be perfectly well defined and have derivatives of all orders along a boundary curve C, but if you change to we're using its derivatives in the interior, if there's a point where they're not defined, then you have a problem. And that's actually what I'm going to make use of in this example. So let's suppose the vector field that we have as components P and Q. So P is minus y squared plus y squared, and this is x over x squared plus y squared. Okay. Now it turns out that F is conservative. That F is the gradient of little f, where little f is equal to arctangent of y over x. So if you were to take the take a partial derivatives of this with respect to x and y, using the fact that the derivative of arctangent of x is 1 over 1 plus x squared, then you would get exactly this. Now, this example seems kind of strange because before I wrote down Green's theorem, I just said, if you're trying to evaluate a line integral, because this is what the problem is about, now let C be a closed curve that's encircling the origin. So it can be any curve whatsoever as long as the point 0, 0 is within the interior. Okay. So then what we want to do in this example is what is the line integral of this vector field over this closed curve? Now, I said before, if your vector field is conservative and you have a closed curve, then this line integral of a work would end up being 0. So I think, well, there's nothing to do here. But it turns out that we can't just go ahead and do that here. So this equals 0 only if f is conservative in all of the interior. So if you have so in this case, we have some closed curve C, and we'll assume that it has a proper orientation counterclockwise. And it happens to contain the origin somewhere in the middle. So, and there's something that I should have made clear in the last section when I talked about line integrals being independent of path. That's what you get when the vector field is conservative, and therefore the line integral over a closed curve will end up being 0. What I didn't make clear was, where do you need the vector field to be conservative? Not just along the curve itself. It needs to be conservative throughout the domain, some domain that contains the whole curve and the interior. So in some domain that contains the curve C and its interior D. Okay. Because if it fails to be conservative, like I said, the line integral, you want it to be independent of path. What if your path takes you through a point where the vector field fails to be conservative? Then all of this falls apart. Now, I've just said that this vector field is a gradient of some function little f. So you might think, what's the problem? Where does this vector field fail to actually be conservative? Where are the relevant functions undefined? At the origin. These are undefined. If x and y are both 0, this is going to be undefined. It's an indeterminate form. So because you have this one point, so then everything falls apart. You can't just say that the line integral of f over this curve is going to be 0. Now, if the origin had not been part of a picture, if I had chosen the curve elsewhere, like up here, where the origin is not part of the picture, literally, then there's nothing to do here. I could say, oh, the line integral is 0, because in that whole domain, big F is conservative. But the origin presents some problems. So we need to do something about that. Okay. All right. So before you use Green's theorem, then you have to make sure that you're not going to have any difficulties because of some points where things fail to be defined. All right. I don't know if I finished this whole thing, but so what I'm going to do is I'm going to poke a hole in this domain. I'm going to make a circle surrounding the origin. And the circle will have, I'll give it a radius A. As long as I can choose any A, as long as it's small enough so that it fits in the interior. And if I choose A sufficiently small, I'll have that. And I need the orientation to be correct. So here, because I want this part out here to be the interior, I'm going to orient the boundary, this interior boundary, clockwise. Again, if you have your little guy walking along the boundary, the interior of a region in question should be on his left. Okay, so now if I remove this hole within this region that's shaded, F is conservative, it's well defined throughout that. So there, I can go ahead and take advantage of Green's theorem. So, okay. So now I could say that so apply Green's theorem to interior with the hole removed. So, okay, if I were to redraw this a bit bigger. All right, so here's my curve C. I'll call this C prime. Actually, call it minus C prime to be consistent with my notes because we have to orient it this way. C is already oriented counterclockwise. Okay. Now, so the line integral because now I have the entire boundary of this region D that's between the outer curve and the inner curve, my hole. Okay. So that would be okay. Now, this is going to be 0. Because F is conservative on D, where D is everything but the hole. Okay. All right. Now, because this is the line integral that I actually want. So because all this is 0, I can say that the line integral over the outer curve is equal to minus the integral over the circle of radius A. But now, if I change back to a customary clockwise orientation, then that changes the sign back. So in other words, the line integral that I actually want, in the first place, the work done by F to push an object along its outer boundary, turns out to be equal to the work done, and this is an integral I can actually evaluate, along the inner boundary. As long as I make sure that now these are oriented in the same way. So minus t prime, that is clockwise orientation. Minus that is going to be counterclockwise. But what is this? This is now a circle of radius A, where A is chosen small enough so that this is contained in here. And now, this is something I can easily do parametric equations of. So I can say x is equal to A cosine t, y is equal to A sine t. And t goes from 0 to 2 pi, as usual. And I think I'm running... Okay. So what you can do is use this, and I'll quickly do the setup. So the line integral over the boundary that I really care about is now the integral over the circle of radius A, and that's going to be the integral from 0 to 2 pi. And what we have here is going to be p dx plus q dy. So here are p and q. So I have minus y of t over x of t squared plus y of t squared x prime of t, because that's your dx, plus q with the parametric equation filled in, times y prime of t dt. So p dx plus q dy. And now you go ahead and fill everything in. But this part right here on the circle, that's just going to be a squared. This too is going to be a squared. When you fill in x of t and y t, you have a big old simplify fest. Really, it's kind of outrageous. You end up getting the integral, everything cancels, literally. Everything cancels and you get 1 from 0 to 2 pi. So you get 2 pi. So when you have a conservative vector field, notice I never said what this outer curve was. It doesn't matter. It encircles the origin. That's the only criterion. So curves encircling the origin, no matter what curve that is, the total work done by this conservative field, vector field, around that curve is always going to be 2 pi. Because you're able to use Green's theorem to conclude that this integral is equal to this one. Because they're boundaries of a region in which the vector field is known to be conservative because you're avoiding that troublesome spot of the origin. So we didn't actually use Green's theorem directly in this case, but it helped us get a simpler line integral that we could use. Now, but Wednesday will be all about more examples of Green's theorem, like what you're going to have in the homework. Okay.
Is that regardless of ring size?
What?
Is that regardless of ring size?
I'm sorry, but the chairs are making too much noise.
Is that regardless of ring size?
Yeah. Oh, yeah. Like the A.
Yeah. Because you said it regardless. I don't want to use the word circumference.
Yeah.
Regardless of curve.
Like how long that curve is in a certain area. Yeah, it's not mattering because for radius, it's because of this normalization here. The radius makes it out.
Okay. Does it have anything to do